We've now come back to trees. This time, trees for predicate logic, for first order logic. And for the kind or degree of first order logic that we're working with, that we can expect to work with for the rest of this semester, these trees still have the same advantages over natural deduction that we observed when using truth trees for propositional logic. Well, let me clarify what I mean by that term, this kind of first order logic, so that I can explain exactly what the advantages are. We've been doing, and we can expect to do, monadic predicate logic to this point in the semester, and except for some other topics we're just going to touch on in the final week. When I say predicate logic, of course, I could also call it first order logic. I could also call it the logic with quantifiers. That's not any surprise, but, or I could call it first order logic. But what needs to be added when we're being precise about the kind of first order logic we're doing is that the predicates in it are monadic. They are one-place predicates. Monadic predicate logic uses predicates and quantifiers, but where the predicates always take one item that they describe. So, ate chicken salad might be a predicate, and there's only one place you can put a name, right? So you ate chicken salad, I ate chicken salad, everyone ate chicken salad, no one ate chicken salad, someone ate chicken salad, and the like. Is a neurosurgeon. You're a neurosurgeon, I'm not a neurosurgeon, everyone is a neurosurgeon. It's not the case that everyone is a neurosurgeon. In each of those cases where you have the predicate, there's exactly one name you can put into it. Or when you have a quantified statement, you have one variable, the X. If N is the predicate, is a neurosurgeon, and you want to say neurosurgeons exist, you would say there exists an X such that NX. Okay. Now, logical predicates don't need to be confined to a single name like that. They can have, you can have two-place predicates. That's the first thing that happens after you get past the monadic. You can have the predicate is the child of, right? So that O capital C A is how it would be written. O is the child of A. Orestes is the child of Agamemnon. And when you're dealing with two-place predicates, of course, within the quantificational scheme, you typically need two variables. So you might, if you want to say someone is the child of someone, you'd say there exists an X and there exists a Y such that X, C, Y. Okay. The reason I spell out the difference between monadic and more complex forms of first order logic is to be precise about what I want to say here regarding trees. Trees, you may recall, are a decidable procedure in propositional logic for determining whether an argument is valid or invalid. When you use rules of inference, you show that an argument is valid by finding the proof that leads from the premises to the conclusion. You make it valid, you display that it's valid. But if you fail to come up with the proof, you have not thereby shown that the argument is invalid. All you've shown is that you fail to prove its validity. With propositional logic, as you recall, you can show with a truth tree either that an argument is valid if it's valid, or equally that an argument is invalid if it's invalid. The truth tree has those paths that are either closed off with an X or left open with a little circle. And if there is even one path left open, it doesn't follow that you're waiting to see. You wonder whether this could be an invalid argument. Oh, no. What you've shown is that it is an invalid argument. That's really quite important. It's a decidable procedure, as of course, truth tables in their clunky way also are decidable. Okay. And for the same reason and in the same way, truth trees in first order logic, when it's monadic first order logic, this does not apply when we get to two-place or more complex predicates, okay? But when it's monadic first order logic, then you can be sure to get an answer, whether it's the answer that the argument is valid or the answer that the argument is invalid. As with propositional logic, the basic idea of truth trees is also the same. We take all the premises of the argument together, and we take the negation of the conclusion, and we ask, in effect, can we have all these at once? Is it possible for all the premises to be true and the negation of the conclusion also to be true? If that's possible, of course, you can't have a valid argument, because the everyday, the homey way of describing validity is that once you have the premises, if you accept the premises, then you're forced, you're compelled to accept the conclusion as well, right? Now, if you could have all the premises and you could also walk around with a negation of the conclusion, why then you wouldn't be forced to accept the conclusion given the truth of the premises, okay? So if you can have a consistent set in that way with all the true premises and the negated conclusion, you would not have a valid argument. If, on the contrary, you have all the premises and then you negate the conclusion and you wind up with a contradiction, as displayed in the tree by all the paths being crossed off, well, then there's no way to have the negated conclusion. You just can't do it. You start with these premises, you can't have the negated conclusion. Therefore, you have to have the conclusion as stated. Therefore, the argument is valid. The thinking behind the tree is the same as the thinking behind the truth table approach. In the truth table, we merely asked, is there any occasion, any configuration of truth values of the propositions that would make all the premises true and the conclusion false? Well, truth trees just turn this around a little bit. They say, well, suppose we take the negated conclusion. Can we have the negated conclusion be true and all the premises be true? But of course, if the negated conclusion is true, then the conclusion is false. So it's the same idea, much more elegantly carried out, as is at work in the truth tables. It's in diagrammatic form, of course. It's not in tabular form. My saying this, my comparing the trees to the tables, might lead you to wonder whether you could use truth tables in first order logic when you have quantifiers. No, there's no way. A statement with the quantifier simply can't be summed up with truth values in the way that an individual proposition can. Maybe that's a reason you'll find to be grateful for quantifiers. Now, the complaint, the dissatisfaction, might be similar in both cases. The complaint or the dissatisfaction might be that although this is a terrific test for showing whether or not the argument is valid. It doesn't display the reason. It doesn't show you what it is about the premises that make the conclusion follow. And in predicate logic, when we're dealing with these quantifiers, we can maybe state that same dissatisfaction, give voice to that dissatisfaction in a more precise way. Now, the normal proofs we do, the proofs in natural deduction for predicate logic, work by, they start with, normally, if it's a pure quantificational argument, they start with all the premises in quantificational form. They're generalizations. They're either universal statements or existential statements. In order for us to work with them, to apply the logical rules of inference or the replacement rules, normally we have to instantiate those quantifiers. When you have an existential quantifier at the beginning of a line, you apply existential instantiation. When you have a universal quantifier, of course, you then go to universal instantiation. Okay. But because typically speaking, the conclusion of one of those arguments also has a quantifier in it, at some point in the proof, you're going to have to go back into the language of quantifiers. So you start out with statements that begin with quantifiers and you see X's in them. And then you give instances, you instantiate, you find, as it were, you're talking about examples or exemplary statements of the same utterance. So where you had for all X, f of X, you go to f of A, okay? And then you look at the logical relations, then you can pretend you're back in propositional logic, as long as, assuming you've set up the argument correctly, you then can generalize, you can apply either existential generalization or universal generalization, and you're back in the language of quantifiers. Okay. And in that sense, you might say the proof by deduction using the rules of inference always reminds you of where you're going to end up. You're coming back to statements with quantifiers before them. Now, while using trees, only half of what I've been saying is still the case. You still have rules for instantiation, EI and UI. What you do not have are rules for generalization. You don't use EG, the existential generalization, or UG, the universal generalization. It's more like you start with these quantifiers, these quantified statements, you instantiate so that you can have a bunch of concrete propositions to work with, and assuming you've done it in the right way, you can then apply the methods that you're familiar with already from truth trees and see whether you wind up with a consistent or an inconsistent set, and then you can conclude without ever having moved back into the language of quantifiers whether or not this argument is valid. Okay, so of course the good news there, the good news about this this difference is that you don't have to learn and use the rules of generalization. Now, beyond the beyond the liberation from generalizations, again, as I was saying, truth trees in this domain of predicate logic display the same two, offer the same two advantages to us that we already saw when we were using truth trees with propositional logic. First of all, they are mechanical, they are algorithmic, they are procedures of a sort that we don't have for the corresponding proofs using natural deduction. We don't have to think strategy. Sometimes it's true that depending on how you begin and move on with a proof, you can have a simpler tree or a bushier tree, harder one to work with, okay? But your decisions are not going to affect the correctness of the answer you come up with. Right? You can have a mechanical procedure for this kind of proof. And as I was saying, you also have a decidable procedure. If it's an invalid argument, you know it's an invalid argument. You don't have only the failure of your proof. Now, I said you still have instantiation. The rules for instantiation are remarkably similar. Well, they're the same as the rules for instantiation in a traditional proof. Universal instantiation, very straightforward. If you're saying for all x, f of x, how do you instantiate that? Well, you can write FA or FB or FC. I hope you see the pattern here. FD. You can put anything because after all, if the universal quantifier is assuring you that this predicate is true for all individuals, then you can put the name of any individual there. One little asterisk coming up. Existential instantiation is different. The most you can say in an act of existential instantiation is that there's some name, right? If it's true that there exists at least one neurosurgeon, then, so we've got, there exists X such that NX, then you can instantiate and say, let's refer to that neurosurgeon. A is a neurosurgeon, and you write NA. But you can't assume that this neurosurgeon you're now talking about is anyone in particular. You only know, thanks to what the existential quantifier means, that there is that there is at least one. Let's call that person A. That doesn't mean you know it's A, you know it's a particular person named A. We're just using a dummy name there. So because we're using a dummy name, then, and for the same reason that this holds true with the natural deduction, you have to use a name that has not already appeared in the proof. Otherwise, you see, you would be helping yourself. You'd be saying, oh, A is a neurosurgeon, and you come along, let's say you have an existential statement that says someone is a car mechanic, right? You say, okay, car mechanic, C, there exists X such as C of X, let's say C of A. So A is a car mechanic. And you say, well, you look at that. A manages to be both a neurosurgeon and a car mechanic. Isn't that an interesting consequence of what we've been saying? It's not a consequence because you can't instantiate in that way. Once A has been used to refer to this neurosurgeon, whoever it is, then the same letter A cannot be used to refer to the car mechanic, whoever that may be. Okay, now we already saw that rule. I already explained that rule in connection with traditional proofs in first order logic. It's the same rule. And then because of that rule, it's also wise, indeed, I would make it a methodological principle, that you apply all possible existential instantiations in a tree before going on to any universal instantiations, okay? The universal instantiations, of course you can use a letter that has already appeared. In fact, almost always that's what you want to do. The only difference, and I said there was an asterisk when it comes to universal instantiations. Now, you know that in a tree, once you've used a line, once you've translated it into something else, for example, or once you've instantiated an existential claim, you check that line. You say, this has already been taken. We can't come back to this line again. When it's a universal statement and you instantiate it, you don't check that line. And indeed, sometimes you mustn't check the line. When you've carried out the branching paths of your truth tree, and there's something that is still open, it remains possible that you can close those paths by going back to one of the universal statements that already appeared earlier in the proof. Okay, let's say one of the premises is a universal statement, and you already applied it. You might think the work of that universal statement is done. Not the case. Sometimes, especially when an existential instantiation introduces a new name into the proof, you find that you have to go back to that universal statement and instantiate again and get those new names into the proof too. When? Well, common sense would tell you you want the predicates to be, at least one of the predicates involved, to be the same as the predicates that are appearing. So you've got a path, and in the path you've got the predicate G. So you've got G of B. And you look up in your premises and there's a universal statement that has a predicate G in it. So because it's a universal, you can instantiate it with B, and then you bring that whole thing down and either branch or stack it, right, in the proof. But there wouldn't be any use to that if the predicate G did not also appear among the premises, that same predicate G that you're trying to close off the path for. Now, in a minute, we're going to do a few examples. I found one simple example done by someone else online. We'll start with that. Then we'll look at some of the kinds of examples you'll find on the homework. Before I do that, let me give my version of the rules to follow. In one sense, there are more insistent rules when we're using the trees because of the decidability of the procedure. By that, I mean this. I've been going on about how nice it is with trees that when the argument is invalid, the tree tells you it's invalid. But for the tree to tell you it's invalid, you have to know you've tried everything. It's not like a case where you just lay out the premise and say, "Whoa, I haven't closed off any paths at all." No, you have to try to close off all the paths you might. So there's a set of rules or steps that you can bear in mind. And if you follow all these steps, well then, and in that case, the persistent existence of some open path in the tree tells you that the argument is invalid. So first, as always, with the truth tree, you list the premises, and below the premises, the negation of the conclusion. 2, you apply any negation rules. When you have a negation in front of a quantifier, you use the CQN, you want to get the negation inside and translate those lines accordingly. Wherever possible and when it's necessary, you apply rules of propositional logic. This is especially relevant if you have two separate quantified statements joined by a connective, like if for all x, mx, then for all x, gx, right? So you've got an if then. Well, you're going to want to apply the branching and the negation in the tree just as you did in propositional logic. Okay, that was step 3, apply the rules of propositional logic. Then step 4, wherever possible, apply existential instantiation. When you have instantiated, you check that line. Of course, you check a line to which you've applied rules of inference too, but this checking is different. If what an existential quantifier gives you is that there's going to be at least one thing, right? There's at least one neurosurgeon. Let's call that neurosurgeon A. If the existential statement gives you that, there's also a way in which it refuses to give you more. There is at least one neurosurgeon. Having used the letter A when you instantiated there exists X such that N X, having used that letter A, you may not go back and also use the letter B. Now, even if B has not yet appeared in the proof, you see, putting a second name in, instantiating that statement a second time, violates the meaning of the existential quantifier, which is that you only know for sure that there's one. There may be more, but you only really know that there's one. So you check that line that has the existential quantifier, and you may never go back to it. Once you have done that, once you have instantiated every existential statement, you have applied EI wherever that's possible, then you apply UI wherever that's possible. Remember in this case, remember when it comes to the universal instantiations, that you may well have to go back when you've seen the same predicate appear in an open path. Now, if you followed all those rules, there's nowhere else that you can apply universal instantiation so that one of the premises has a predicate in it relevant to the predicate, or that's equivalent to the predicate in an open path. You've tried everything. You've exhausted all the possibilities available in this proof, and you still have an open path. Then the argument is invalid. If, however, of course, you're not going to keep going on asking, can I do more, once you have closed all the paths. Once all the paths are closed, then the argument is valid. Okay. And today, rather than continue in the old method of writing physically, I've got some files to exhibit truth trees that I'm going to screen share. Okay. Karen Howe is someone I don't know personally, but she evidently has a very useful website that gives a slightly different version of the tree method. But here's a first example we can use of trees for monadic predicate logic. So premise one, for all x, if f of x, then not g of x. Premise two, there exists x such that hx and gx. And the desired conclusion is not for all x, if hx, then fx. Okay. In this tree, you see, Karen Howe has begun with the premises and the negated conclusion. All right. I'm now experimenting with this. You notice, by the way, these lines have all ended up being checked. Well, they don't start out being checked. They have to be checked when they're translated in some way. Although, I don't see why you'd want to check the first premise. Let me just confirm that. Well, all right. So first, the rules of negation are applied. It had been a negated universal statement. It becomes just a universal statement. And then we get an instantiation, an existential instantiation in this next line from there exists X such that HX and GX, we can write HA and GA, okay? That's checked, or the existential statement is checked. From the first premise, we get if FA, then not GA, all right? And from the negated conclusion, if HA, then FA. I have to correct something I just said. Notice, although I don't recommend this, I was wrong to worry that Howe had checked the first premise. That was just hidden on my screen, not on yours. As here, she does not check this universal generalization. She merely instantiates it. She's prepared to come back and put a different name in if necessary. All right. So now we have 3 lines without quantifiers. What follows is really pretty familiar from the rules of truth trees. We go to the one conjunction. That's the easiest place to start. HA, GA below it. Then using the rule for branching and negating that we have from conditional statements, not FA, not GA. The not GA path closes. Okay, then we've got not HA and FA. Those paths both close. And we wind up with the proof that this is a valid argument. Okay, that's a simple example, mind you, but that's the essence of how a truth tree works with quantifiers. Now let's try one of the kinds of examples that we may find on the homework. Not that one now. Sorry. I keep seeming to bring the same one. This is a good one. Now this is a rather complex one, and because I want to leave time for another more important example, I'm not doing this one all the way to the end, although we're practically to the end. Okay, but I like this example because it has a number of fairly difficult premises to deal with, right? A negated existential claim, PX and QX, and RX if and only if TX, all right? Now what do? We've got the intended conclusion, we negate it. We then go through and clear up all the negations we can find. So, for example, in line 7, the negation rules are applied to line 6. So we check line 6. We're not going to go back to that. In line 8, likewise, we have for all x, not px or not qx or not parentheses rx if and only if tx. All right. We check line 3 because we do that in 9. And then we check line 4. All right. Now, what we end up with are mostly universal generalizations and one existential. Okay. So we're going to begin with the existential instantiation, QA and not TA and not BA. Let me go back to that now. There we are. We're back at the same one. Now, you see where you branch. Let's see, I went to premise 10 to branch. I then went to line 9 because two of those paths closed. I then had just line 9 and I brought that disjunction down, not AA or SA. I then went to line 8, which was a 3-part disjunction within which was a negated biconditional. Okay. This doesn't quite finish on a single page, but it is a valid argument. And I just wanted to show how we do such a thing in a simple case. It's a simple case in one respect. It's a simple case in as much as we only have one existential quantifier in that set of premises. Therefore, we're only going to wind up with one name, the letter A, in this entire proof. It essentially becomes a proof in propositional logic because if you wanted to, for example, people do this sometimes. You see it in the example that Karen Howe gives, although she can do it there because it's such a simple example. But if you wanted to, you could begin by instantiating everything. So you'd wind up with a bunch of statements all in propositional logic and then apply a truth tree to them. Okay. That's not always possible. And this example that I want to look at now is a case in which you have to go back to a universal statement and instantiate from it as well. Actually, you find this particular proof among the exercises in the homework. Premise 1. If there is at least one F or there is at least one G, then at least one thing is not H. For all X, HX or PX, there are no X such that PX and QX, and the desired conclusion is if all X's are Q, then all X's are not F. Okay. Now we begin by negating the conclusion. All right, so we have the negated conclusion, which is for all X, QX, and not for all X, not FX. Okay. We want to apply the negation rule to that latter part, okay, which means we check that line. I now learn how to make a check sign. Okay. And we also apply CQN to line 3, which had a negation in front of it. We make that for all X, not PX or not QX, just applying De Morgan's, of course. In line 1, in premise 1, we have connectives, as you might say, outside the quantifiers. They're not within the quantified statements. Okay. So the first thing we have to do is work with those connectives wherever they appear. And what I did in line 7 was to apply CE. You remember the conditional exchange replacement rule. So CE gives us, there does not exist X such that Fx, and there is no X such that Gx, close parentheses, or there is an X such that not Hx. That too was simplified into line 8, so that we have for all X not Fx and for all X not Gx, close parentheses, or there is an X such that not Hx. All right then. Let's see, what did we do next? From that, from line 5, which was just the negated conclusion, we simplify. Line 5 is a conjunction, and I find it easier to treat a conjunction of quantified statements as 2 lines. So we have, there exists X such that Fx, and for all X, QX. And now that we have the negations gone, and now that we've applied the following step of taking care of the connectives, why now we can begin to instantiate. What do we do first? Existential instantiation, of course. There's only one freestanding existential statement, that's in line 9. And so we instantiate it with the letter A, we get FA. The universal instantiation, right, just becomes QA. We use the same letters wherever that's possible. And then from line 6, which was a universal statement, we write not PA or not QA. Okay, forgive these inadequate diagonal lines. They're the closest I was able to approximate to. But you've got FA and QA stacked and not QA on the right, so that path has already been closed off. Okay. Hmm. Okay. Well, I discovered, I'm discovering so much. Okay. Ah, we're back at, we're back live. I want to just say what we're doing before I return to share that screen. I've begun to instantiate, and what happens from here on out is first that I'll exhaust all possible applications of the letter A. Then it's going to look like some paths remain open. In response to that fact, I go back and start instantiating the letter B into some lines as necessary. Okay. Yes, here we go. So having the not PA open here, I then went to line 2, instantiated that as HA or PA, and one of those paths closed off. Now at this point, you start asking yourself, well, what can I do? I've got an HA. Above that, I've got a not PA, QA, FA. All right. Well, I'm going to look for something that has, among other things, not HA. I see that in line in line 8, we have a conjunction of two universal statements, then a disjunction of all that with an existential statement and the not HA. So what I've done here is to bring those down. Oh, I erroneously brought the existential statements, the negated existentials down from line 7. I should have brought the lines from the universals from line 8, but it doesn't matter because all I wanted from those two universal statements was the negation of FA, and I got that. The negation of FA, that path closed. Now I have an existential statement over here, not HX. You'd think all is well because you've got an HA and you can make that not HA. Of course you can't, because that would be going back to an existential statement and giving it a particular name. You can't do that. You can do a not HB. Well, you think that's no good to me. Not HB doesn't negate HA. No, but there might be a place we can find an HB, namely the same place we found HA, which was up in line 2. So we went back to line 2 for all x, hx, or px. And thanks to universal instantiation, we made that HB or PB. That's why now, this is not something you write yourself. I'm writing it to illustrate the point. I wrote UI2 again. You not only may, you often must go back to a universal statement and instantiate again. This time, looking for that letter you wanted. So you have HB, PB. The HB, coming as it does below the not HB, gives you a closed path. What about the PB? Well, you don't even have to look up the paths to see whether you're going to find a negation there. For you haven't had a B in anything. Okay, so what you need to do is find a universal statement in this proof among the premises that has a predicate letter P to which you can supply a B. Okay, well, it can't be, let's see. Well, we've got premise 3, which we turned into line 6 here, for all x, not px or not qx. All right, so we put B in, not PB or not QB. Okay, close that path, and now we've got a not QB. Can we find a Q? Yes, we're in luck because of line 10, which was a simplification from the negation of the conclusion. We have for all x, QX. Good thing we didn't check it. Good thing we mustn't check it. If for all x, QX, then of course, QB. We write QB by itself and we can close that path. Okay. Well, as always, we have some technical glitches. First there was the chalkboard, then we tried again with the drawing pad. I thought all our problems were over now that we have migrated to the new technology. Not so easy. Nevertheless, I hope you see how a proof like this works. It gets a little complex in that last example I just looked at, right? It gets a little complex because you have to keep going back. The tree doesn't round off quite that quickly. Nevertheless, people often find proofs, even in monadic predicate logic, to be easier with trees than with rules of inference and replacement rules in the applications of natural deduction. Now, for my part, this is just me describing my preference. What I particularly appreciate about trees is that we don't have to deal with the sometimes tricky rules governing universal generalization in a proof of predicate logic. That is, when you have to flag the A you're putting in. To my mind, that says, well, okay, I can do it this way. It's a special method. It's a special proof style. But then we verge on taking on too many rules that all have to be borne in mind. The truth trees have, as always, the advantage that they require a minimum of rules and a minimum of strategy. Well, they probably require a maximum of space, to be frank. Drawing out the lines like that doesn't leave you with a nice numerical kind of proof. On the other hand, even back in 1879, when Frege introduced his Begriffsschrift, and he had a method of proof, it was a kind that has not persisted. Later logicians found much smoother ways to carry out the proofs, and his had a lot of lines to show the rules of inference. The publisher complained that you're going to waste too much paper doing even a simple proof using Frege's notation, to which he rather icily responded, "The publisher's convenience is not a summum bonum." Well, that's as may be. You have to be Frege to get away with that. I'd love to say, with respect to truth trees, oh, the publisher's convenience is not a summum bonum. But I will concede that one uses up more paper, takes up more space doing these proofs. Nevertheless, and as we saw in propositional logic 2, we've got a method here that will always give an answer, and that, barring clerical errors, can always be applied without need for strategizing or what is sometimes called imagination. Thank you.